Hello, welcome to module 34 of the course on application of spectroscopic methods in molecular structure determination. We will continue with ultraviolet spectroscopy in this module also. The earlier module we talked about ultraviolet spectroscopy of olefinic compounds and carbonyl compounds, the effect of conjugation, the effect of oxochrome and all those things we discussed. We will start with the aromatic system in this particular module. Aromatic chromophore is an important chromophore which can be readily identified by ultraviolet spectroscopy. This is a pictorial representation of the molecular orbitals of benzene itself, and the first three molecular orbitals of the bonding molecular orbitals, and the top three molecular orbitals are the anti-bonding molecular orbitals. The first pi1 molecular orbital does not possess any node, whereas the second and the third molecular orbital possess one node which is represented by the red dotted line. It passes through these two atoms which are the nodal point, passes through the midpoint of this carbon-carbon bond and this carbon-carbon bond which is the nodal point in this particular case. As you go up in the molecular orbital picture, the number of nodes increases. This has two nodes each, for example. These are degenerate energy levels. In other words, pi 2, pi 3 are degenerate, and pi 4 and pi 5 also degenerate, and these are antibonding molecular orbital. Finally, pi 6 is an antibonding molecular orbital of highest energy in this particular case. In terms of the electron filling, the degenerate levels gets filled. The lowest electronic state gets filled, and then the degenerate level gets filled. And if you are to talk about the electronic transition of benzene, you can talk about the pi to pi star transition between these two levels, or between these two levels, or between these two levels and these two levels. One can also talk about the pi to pi star level which is corresponding to this particular level here. In other words, benzene is expected to show only one line if all the energy levels are going to be degenerate and the distances or the energy gap between them are equivalent in terms of the this energy difference is equivalent to this energy difference because of the degeneracy and so on. However, benzene gives distinctly three different types of absorption band as it is shown here. This is corresponding to the benzene electronic spectrum. There is a band around 184 nanometer or so. There is another band around 200 nanometer which is this particular band, and finally there is a third band which is a vibrational structure is very clearly seen. The fine lines that you see in the spectrum are essentially due to the vibrational level of the benzene electronic transition. So this is explained by taking this particular energy level diagram where you have various electronic levels of the pi system. All of them correspond to pi star. Some of them are symmetry forbidden and some of them are allowed. The 180 nanometer is the most intense transition, which is a symmetry allowed transition, whereas the 204 nanometer and 254 nanometer are forbidden in nature. So the forbiddenness essentially causes the decrease in the intensity of that particular transition in the benzenoid compounds. Now when benzene is substituted with oxochromes like for example iodobenzene, phenol, phenoxide and so on, the functional group are essentially oxochrome. There are two effects that it does. One is that it shifts the aromatic absorption maxima to longer wavelength. As you can see from benzene, it is going from 204 nanometers to 226 nanometers. By the time you come to nitrobenzene, for example, the pi to pi star transition goes to 254 nanometer. It's interesting to see that the aniline essentially shifts the benzene absorption by oxochromic effect of the ammonium functional group from 204 nanometer to 230 nanometer, essentially because of the participation of lone pair of electron on the nitrogen onto the aromatic ring. However, if the lone pair is protonated, the spectrum essentially appears like a benzene spectrum. This is 204 and 254, whereas anilinium ion is essentially like a benzene kind of a structure, 203 and 254. In other words, the oxochrome effect is diminished once the nitrogen lone pair gets protonated in the case of aniline to anilinium ion. So this is essentially illustrate the oxochrome effect of the various substitutions that are present in the benzene ring, causing the shift of the wavelength to go to higher wavelength region in the case of pi to pi star transitions of benzene. However, steric effects can inhibit the oxochrome effect. That is what is shown in this particular system. If you take benzene, it has an absorption around 204 nanometer. On the other hand, if you take biphenyl, the corresponding transition, aromatic pi to pi star transition, is shifted to 246. In other words, one of the phenyl group acts as an oxochrome group for the other phenyl group, causing the transition to go to at longer wavelength of 246. Now, if you have additional methyl groups, that also can have the oxochromic effect. So it is further shifted to 267 nanometer, but this is expected to have even much longer wavelength, but that longer wavelength effect is not seen here clearly, because this essentially behaves like trimethyl benzene only. The effect of this particular oxochrome, namely the trimethyl substituted phenyl oxochrome, is not felt on this particular ring or vice versa. In other words, this is like a simple trimethyl benzene spectrum is what is seen. This is because you have the ortho substituents which are going to make these two phenyl ring out of plane with respect to each other. So the delocalization of electron, extended delocalization of electron, is not going to take place because of the steric inhibition of the methyl groups which are present in the ortho functional group. This is better illustrated in the case of nitrobenzene. Nitrobenzene has an absorption maximum of 254 nanometer, corresponding to the pi to pi star, the lowest energy pi to pi star transition, for example. When you introduce a methyl group, it is shifted to 250 nanometer, and the intensity is also reduced to 5950 from 8620, which is the epsilon value. The numbers that are given in the parenthesis are the epsilon value or the extinction coefficient value of these transitions. Now, when you have an isopropyl group, that is even a bulkier group which puts the NO2 out of plane with respect to the aromatic ring, the oxochrome effect will be felt only if the NO2 is in plane with the aromatic system for the electron withdrawing effect to take place, and if the nitro functional group is orthogonal or at a different angle with respect to the dihedral angle of the nitro group and the plane of the benzene ring is different, then the effect will not be felt. In fact, the effect is diminished 250 to 247 nanometer. When you have a tertiary butyl group, finally, it is not even seen as a lambda max. It appears as a shoulder in the 200 nanometer band, and the epsilon value considerably decreases from 3660 to 1450 or so at 250 nanometer range of this particular spectrum. If you take NN dimethyl aniline, the NN dimethyl amino functional group is the oxochrome. When you introduce an ortho methyl substituent, the nitrogen lone pair cannot be in plane with the aromatic ring, so the delocalization is inhibited. Steric inhibition of delocalization is what takes place. So as a result of that, the effect is the bathochromic shift. The effect is a hypsochromic shift is what is being seen to go to the lower wavelength region from 254 to 248 nanometer in this particular case. On the other hand, if the two functional groups are not sterically hindered and they are further away, as in the case of the para disubstituted derivative, and if one of them is an electron donating group and another one is an electron withdrawing group, you can observe intramolecular charge transfer band in the aromatic system. That is what is illustrated in this particular table. If you look at the table carefully, the oxochrome effect is very clearly seen, going from benzene at 254 to phenol 270, aniline 280, and nitrobenzene 269, measured in this particular case, I believe, in ethyl alcohol as a solvent. And the second substituent not only adds to the bathochromic shift of the system, on the other hand, it not only adds to the bathochromic shift of the pi star transition. When you have an electron donating and an electron withdrawing functional group in conjugation with each other, you can write a resonance structure which corresponds to the charge transfer structure. That is one of the reasons when you take, for example, either the para-nitrophenol, which is this particular molecule, or para-nitroaniline, which is this particular molecule here, the wavelength of pi star transition essentially comes to the visible region. In other words, para-nitrophenol is a yellow color substance, para-nitroaniline is a deeper yellow color substance, whereas phenol, aniline and nitrobenzenes are practically colorless. I mean, nitrobenzene is sort of pale yellow, but phenol and aniline are practically colorless liquids. And the color essentially is happening because of the shift of the wavelength to longer wavelength region, which is essentially because of the intramolecular charge transfer, which is represented by the canonical structures that are shown here. In addition to the bathochromic shift, one can also see the hypochromic shift in terms of the epsilon value increasing considerably as you go from benzene to para-amino nitrobenzene, for example, has a maximum hypochromic shift in terms of the epsilon value increasing by 2 orders of magnitude corresponding to the benzene itself. Now, as we go from the benzene to higher polycyclic aromatic ring system, there has a progressive shift of the pi to pi star transition in the aromatic system because of the extended conjugation that is present here. This spectra shown here correspond to naphthalene, which is in the violet color. The green color is the anthracene spectrum, and the blue color correspond to the tetracene spectrum. You can see here the longest wavelength pi to pi star transition, all of them show vibrational fine structure. In addition to that, you also have the higher energy bands, which are the pi to pi star transition, allowed pi to pi star transition of this aromatic system. So the message here is that as you increase the conjugation and go to linearly fused longer acene systems, the wavelength gets shifted from the ultraviolet to near the visible region. So much so that when you go from the benzene to pentacene, for example, benzene is colorless, naphthalene is colorless, anthracene is also colorless, tetracene is sort of reddish orange in color, pentacene is also bluish in color in terms of the color that is appearing, shifting the wavelength of pi star transition into the visible region as you progressively increase the conjugation effect of the aromatic system. The conjugation effect is also used for distinguishing the cis and trans isomer. The trans isomer is supposed to have least steric interaction. In other words, this aromatic ring and this aromatic ring can be in conjugation with the pi system. So through conjugation is possible, and that puts the pi to pi star transition at a longer wavelength compared to a cis isomer. In the cis isomer, because of the steric hindrance, both the benzene rings cannot be in plane with the pi system, the carbon-carbon double bond here, the central carbon-carbon double bond. Because of steric hindrance, one of the phenyl group will be out of plane. So the through conjugation is not as effective as in the case of the trans isomer. So the wavelength of absorption, for example, if the trans stilbene is 295 nanometer, and also epsilon is almost twice that of the cis isomer. The cis isomer has an absorption around 283 nanometer. So essentially one can distinguish, if both the isomers are available, then one can distinguish by comparing the two spectra of these compounds. The one that has a longer wavelength region, absorbs in the longer wavelength region, would be the trans isomer. The one that absorbs at the lower wavelength region will be the cis isomer in this particular case. The cis-trans isomerism distinction is clearly seen in the case of trans stilbene. Cinnamic acid also shows the same effect. The trans-cinnamic acid is 272 nanometer. Here the extended conjugation is all the way up to the carbonyl functional group of the carboxylic acid. The cis-cinnamic acid has an absorption around 285 nanometer. What is even more important is the hypochromic shift of the trans isomer in comparison to the cis isomer in terms of the epsilon value being about 1.5 times more than the epsilon value of the cis isomer. This is the phenyl butadiene. In the case of phenyl butadiene, this is a trans isomer and this is a cis isomer. Once again, trans isomer has a longer absorption wavelength with a higher extinction coefficient compared to the cis isomer, which has a lower wavelength absorption and a lower extinction coefficient also. Now, apart from the pi to pi star transition, one can also look for intermolecular charge transfer transition. Earlier we saw the example of intramolecular charge transfer. Here the charge transfer is essentially the electron hopping from one end of the molecule to the other end of the molecule. That is why it is called the intramolecular charge transfer transition. One can observe the intermolecular charge transfer transition also, provided a donor molecule and an acceptor molecule come close to each other. What is an electron donor? Electron donor are substances which are electron rich in nature with low ionization potential, whereas electron acceptors are substances which are electron deficient in nature with very high electron affinity. That is what the characteristic feature of the electron donor and an electron acceptor. Electron donor should be low ionization potential molecule. Electron acceptor should be high electron affinity molecule. The interaction between a donor and acceptor can result in the formation of a charge transfer complex. This is a pi complex kind of a system is what we are referring to often, and this is essentially known as the charge transfer complex. They have characteristic absorption band called the CT band. Now if you take the highest occupied molecular orbital of the donor, which is this particular, which is a occupied filled molecular orbital, so it is highest occupied molecular orbital donor. The lowest unoccupied molecular orbital of the acceptor, which is shown here, which is an empty molecular orbital. When they come in close proximity to each other, there is an energy level which is created, which is characteristic of the molecular orbital of the charge transfer complex itself. So this will be the HOMO of the charge transfer complex, and this will be the LUMO of the charge transfer complex. Essentially, the charge transfer band is the transfer of electron from the highest occupied molecular orbital of the CT complex to the lowest unoccupied molecular orbital of the CT complex. So when the donor and acceptor come close proximity, there is a charge transfer complex formation with an accompanying new band corresponding to the CT excitation. When that particular wavelength is used for exciting the molecule, it causes an electron transfer from the donor to the acceptor, forming the donor cation radical and an acceptor anion radical. An example of such a process is what is given here. Let us first go with the donors and acceptor, the characteristic molecules which can act as donor: hexamethyl benzene, anthracene. Any aromatic system without any electron withdrawing functional group would be a donor. On the other hand, if you have electron donating functional group like the dimethyl amino functional group, that will be a good donor in nature. Electron acceptors will make the molecule electron deficient in nature. So quinoide compound, tetracyanoethylene kind of a compound, or trinitrobenzene kind of a compound can be acceptors in terms of having high electron affinity in this system. Now if you take this spectrum, the first dotted line spectrum corresponds to the chloranyl spectrum itself. In other words, chloranyl has an absorption around 340 nanometers or so, corresponding to the pi to pi star transition of chloranyl. When chloranyl is mixed with paramethoxytoluene is a colorless substance, whereas chloranyl is a pale yellow substance. When these two are mixed together, a bright orange color is what is seen in the spectrum. And this is because of the formation of a charge transfer complex, the donor, which is a paramethoxytoluene, and the acceptor, which is the tetrachlorobenzoquinone, which is chloranyl, for example. This band is a unique band which corresponds to the species that is produced by mixing this with paramethoxytoluene. So this is the charge transfer absorption band corresponding to about 500 nanometer lambda max. And this band is not present either in the either of the starting material, namely the paramethoxytoluene or the parachloranil, for example. This is formed only when these two substances are mixed because of the formation of the charge transfer band corresponding to the formation of the charge transfer complex. Now, photochemistry is closely associated with electronic absorption spectroscopy, for example. Electronic absorption spectroscopy can be used very conveniently for following certain photochemical reaction. Let us take the example of this particular phototransformation. This is a spirocyclic compound, and this spirocyclic compound has an absorption maxima around 367 nanometer. When this molecule is irradiated with the wavelength of radiation 365, it essentially undergoes the molecular excretion of molecule of nitrogen and carbon monoxide to give cyclopentanone. Cyclopentanone does not have any absorption in the region the starting material is absorbing. So cyclopentanone has an absorption typically in the vacuum ultraviolet region of less than 200 nanometers or so. So if one wants to follow the kinetics of this particular reaction, one can take this substance of known concentration, irradiate the substance and follow it by spectrophotometry, because the band at 360 nanometer will keep on decreasing in the intensity because of the decomposition of this molecule to cyclopentanone. Cyclopentanone itself does not absorb in this region, so the decrease in the intensity of absorption can be quantified using the Beer-Lambert's law, and hence the kinetics of this kind of a photochemical reaction can be easily studied using ultraviolet visible spectroscopy. Another application of ultraviolet visible spectroscopy is shown here. Enzymatic hydrolysis is often followed, or any enzymatic reaction is often followed by spectrophotometry as a technique. An illustrative example is shown here. The R group may be a large protein or a DNA kind of a molecule to which a paranitrophenolic 2,4-dinitrophenolic group is attached, for example. If one wants to study the hydrolysis by means of a hydrolytic enzyme, this can be done using the spectrophotometry. The aqueous solution with the buffer of 4.2 is what is taken in this particular case. When the molecule undergoes hydrolysis, this molecule the 2,4-dinitrophenolic derivative has an absorption around 300 nanometer, not more than 300 nanometer. On the other hand, once it is hydrolyzed under the conditions of pH of 4.2, buffer solution of 4.2, this exists as the phenolate anion. The phenolate is a strong oxochrome, and it causes the shift to about 100 nanometer shift to the lambda max of this particular species is 430 nanometer. So as the hydrolysis proceeds, the absorption around 430 nanometer will keep on increasing until it reaches a saturation of complete conversion to the phenoxy species here. So if one wants to follow the enzymatic kinetics, hydrolysis kinetics, one can just observe this species and quantify the species present in the solution, because the species epsilon value can be easily measured by making the pure phenolate from the phenol and the sodium hydroxide solution, for example. So the quantification and the kinetic measurements can be easily done using spectrophotometry. This would be a true application of the quantitative aspect of the spectrophotometry in this particular case. So what we have seen in this particular, the last two modules, is that as a standalone technique, UV visible spectroscopy has very limited use in structural elucidation problem. But when it is put together along with infrared and NMR spectroscopy, it can be used for ascertaining certain functional group like carbonyl, unsaturation, and aromatic chromophores. Of course, IR and NMR can by themselves tell about the presence of carbonyl functional group and aromatic functional group. This will be an additional information that one can obtain from the UV visible spectroscopy. We also saw examples of cis-trans isomers being distinguished by comparison of the spectra. Unless you have both the samples of cis isomer as well as the trans isomer, the comparison becomes difficult. If you have only one isomer, it is not possible to distinguish based on the spectroscopic data. By itself, it is a very powerful tool for quantification purposes using Beer-Lambert's law. In other words, using the Beer-Lambert's law, one can quantify the substances that are present in a solution using the spectrophotometric technique. Spectrophotometry is very widely used in the kinetic measurements, for example. So we saw one or two examples of the application of the quantitative aspects of UV visible spectroscopy in measuring the kinetics of the chemical reaction, either photochemical reaction or a thermal reaction. The enzyme kinetic measurement is one application of the UV visible spectroscopy. I hope you enjoyed this particular module. Thank you very much for your attention.